Okay, so good morning, everyone. Yesterday we have started with design of absolute loader, how the text card and transfer cards are loaded. So we have saw that with the help of an flowchart algorithm, you can say. And then after we had discussion on subroutine linkage, why we require subroutine linkage. With the help of extern and entry keywords, we'll be able to resolve that subroutine linkage issues. So whenever your program is giving call to other procedures, you will be able to link that procedure name with the help of extern keyword. So error issues will be sorted out. After that, we had discussion on dynamic loading, why dynamic loading is useful and how it helps us to save the space. And to achieve dynamic loading, we have to take the help of overlay structures. So overlay structures helps us to analyze dependent and independent modules. So likewise, we have finished these 4 or 5 points yesterday. Today we are moving towards the concept of dynamic linking. So as we know, dynamic loading means on demand. Whenever you need one of the method or function from a library or one of the procedure, that time you are loading that particular part in a memory. Once its use is over, again space will be free. So same way we can use the start concept of dynamic linking. Your application will be dependent on other modules which can be linked on the demand basis, dynamic basis, you can say. So that's just a concept, and there are next two loaders which will help us for a dynamic loading and linking concept, both the things. So as I said, main program contains call for procedures or methods or functions, but that procedures never executed unless and until you're giving call to that, right? So here they are never executed because of condition which never generate true results. Maybe a dead code you can say, or that particular location is not reached. So the loaded program will create overhead. Even though you are linking it and it is not used in your program, then already you're wasting your time and you're having overhead of linking that subroutine. That's the one cause. Second cause, even though you are linking and it will be used, unless and until call is made for that, you won't be able to execute it. So that again motivates us for dynamic linking concept. So we have to reduce the programmer's burden or overhead created at the time of loading and linking when you translate the code. So we can postpone loading and linking till we require it, till our main application demands it. So that is until execution required, we will postpone its loading as well as linking. So this concept is called as dynamic linking concept. So on demand, when you are making procedure call, at the same time linking will be done and that module will be loaded in a main memory. Okay. So this concept dynamic linking and loading is provided with next two loaders called as relocating loader and direct linking loader. So we'll see them one by one. So here you are both are the type of your dynamic loading and linking concept. So relocating loader means loader is having ability to relocate the programming addresses. Means if your starting address changes, your loader can adjust rest of all addresses. So that ability is available with the loader along with dynamic loading and linking. So the main drawback of absolute loader we know it's reassembly. If you make any changes, if you increase the length of any of the routine, you need to reassemble all the remaining subroutines, okay, so that you can replace them with a new addresses and which we can utilize during the execution. So reassembly, retranslation, these problems can be sorted out with the help of relocating loaders, and that's the reason these relocating loaders are introduced. So here, instead of giving addresses for each routine by programmer can choose any address, and your loader can change addresses as per the availability in a memory. So you're not allocating absolute locations to your data or programs. Rather, your relocating loader will choose any of the location which is free and it will adjust all the address dependent constants. So that problem is solved with the help of your relocating loader. So the example of relocating loader is binary symbolic subroutine, BSS loader. BSS loader is a type of relocating loader. Okay. So BSS and direct linking loader both are the type of relocating loaders. So BSS stands for binary symbolic subroutine. Many time MCQ questions will be asked what is BSS. So it is binary symbolic subroutine. These kind of loaders are used in IBM machines. So IBM 7094 series, IBM 1130 series, GEC 35 or UNIVAC 1108. These are just a name for your reference. Okay, so that you'll be able to understand. Okay, then BSS loader is having specific criteria, or you can say constraint. Every instruction will occupy 4 bytes of length, 4 bytes of memory. Okay, that you have to remember. Every instruction occupies 4 bytes of space. Sorry. So if you're using RR type of instruction, and you guys are well aware, RR will occupy only 2 bytes of memory. Like 1 byte is utilized by your opcode, rest of the byte is utilized by both the registers. But here BSS demand every instruction should be of 4 bytes. So rest 2 bytes will be wasted for that RR type of instructions. Okay, but it will occupy 4 bytes. So that is the need of relocating loader. The person who have developed that loader, BSS loader, they have made it fix that your instruction length will be of 4 bytes only. So obviously it will not be able to handle your 6 byte instruction, 64 bytes of instruction. 64 bits, sorry. So BSS loader allows you to use multiple procedure segment, but only one data segment is allowed. So you can have multiple subroutines or modules which will be written in different programming languages. So they are acceptable by this loader. But data needed by all those routines should be kept in one data segment. So multiple code segment, but one data segment is allowed over here. So let's see how this BSS loader works. Theoretically, I taught a lot of things. Now let's see how practically it works. So the abstract view of BSS loader I'm showing right now. Suppose your source program is given to your assembler. Assembler is having ability to relocate the code, object code. Okay, so it will generate the object code which will be translated based on your assumption, whatever starting address given in your source program. Along with object code, your relocating assembler provides additional information. Okay, that will be referred by other programs. And along with this, it generates additional databases. So it will be having 4 different informations. So it will provide how to relocate the program. So relocation information is passed on for relocating loader. Transfer vector, I'll tell you the format of each of this one by one. So just right now understand the meaning of each. If my starting address changed, I have to relocate all the address dependent locations. I always used to give an example. If you are changing your address, you have to update all the bank account addresses, right? Same kind of, they are dependent. If you change your mobile phone number, if you have changed it, so you have to update everywhere wherever you are using it for OTP or online banking purpose, right? I hope I'm connected to you. Then transfer vector. Transfer vector is helping you for linking purpose. I'll tell you the format of it. Now, how many bytes are occupied by your transfer vector? So that is called as length of transfer vector or length of TV. And then original program, object code length. So these are the 4 different information passed on by your assembler. And this info is utilized by your relocating loader. So along with object code means your assembler is not only generating object code, it is providing additional information for the loader. So let's see how this information can be utilized. So relocation bits, it is, as I mentioned, it is used for relocation purpose, adjusting all address dependent constants. Transfer vector is used for linking purpose, linking with all the external subroutines. Then length of the program, that will help you to choose a main memory block, free memory block, where you can load that program. So how many bytes of data you are going to load? So that is the info given here, length of original program, which is used for allocation purpose. And the last bit is loading done by the loader. So once you have set all those things, utilize all those things, you'll be able to load the entire program in a allocated space. So how the relocating means your assembler generates the output for your relocating loader. So as I said, it provides relocation information. So relocation information is coming in the form of bits. 2 bits are used. I'm not talking bytes. It is 2-bit information. So 2-bit informations help us to adjust all the address dependent constants. In this instruction, where you wanna do the relocation, where relocation is required and where not. So that info is given by relocation bits. So each instruction of your program will be associated with relocation bit. 2 bits will be allocated for each instruction. And then object code transfer vector helps you to connect with our external subroutines and the length of transfer vector. So transfer vector is again occupying additional space on top of your object code. Okay, that's why separately you have to specify how many lengths, how many bytes you are going to use for transfer vector. Each entry of transfer vector is also a 4-byte again. And length of object code you know very well. It helps you to allocate the memory. And now let's understand how these relocation bits are distributed in instruction. Your instruction is of 4 bytes. Out of these 4 bytes, where the relocation is expected, that info is given by 2 bits. So assembler provides this information for each and every instruction. So we call them as a relocation bits. So as I said, you're using 4 bytes of instruction. Per 2 byte, 1 bit is allocated. So 4 bytes of instruction divided in 2 halves, 2 bytes of fields. So first 2 bytes will be identified by first relocation bit and last 2 bytes are identified by second relocation bit. So I'll show one diagram which will help you to understand here. Okay. So suppose your instruction is of 4 byte given here, right? So first 2 bytes, see here, out of 4 bytes, first 2 bytes are identified here and one relocation bit B1 is allocated to that first 2 byte. It will represent this 2 byte. So this B1 will identify whether you require relocation in first half of your instruction. If no, it will be 0. And for last 2 bytes, second bit is allocated B2. So it will identify whether you require relocation in last half or not. Okay. So B1 and B2 will have either value 0 or 1. B1 can have value 0 or 1. B2 can have a value 0 or 1. So with this combination, your relocation bit can have the information 0, 0, 0, 1, 1, 0, 1, 1. So 4 possibilities are there. If my first bit B1 is 0 as well as B2 is 0. So 0, 0 means current instruction don't require any relocation. It is independent on the address, right? So when the bit is set to 0, it says that particular bytes are not dependent on memory location, starting memory location. So no need of relocation. If it is set to 1, that specific bit is first 2 bytes needs a relocation. Same way B2 is 0 means last 2 bytes don't need any relocation. B2 set to 1 means last 2 bytes needs a relocation. So there are 4 possibilities as I said. 0, 0 means both first 2 bytes as well as last 2 bytes both don't read any relocation. So complete instruction is not dependent on memory address. If your first bit is 0 and second bit is 1, B1 0, B2 1, it represents second 2 bytes. Here you need a relocation. First 2 bytes में relocation नहीं चाहिए. If you keep first as 0 and second, first as 1, first bit B1 is 1 and B2 is 0. Means what? First 2 bytes of data needs a relocation, but last 2 bytes don't need it. And 1 1 means both first 2 bytes and last 2 bytes both needs a relocation. So entire 4 bytes of data need to be relocated. So this is how you will be able to identify where the relocation required using relocation bits. So it is helping you for relocation purpose. So any question related to relocation bits? They are helping you to identify each and every instruction, whether any address dependent value involved or not. If yes, you have to set accordingly. And this info will be generated by your assembler. So do you have any queries in relocation bit? Or everyone have understood? Yes or no? Everyone is able to understand the significance of relocation bits? Am I audible, guys? Om, am I audible to you?
Yes, ma'am.
Okay. Aniket, have you understood relocation bits?
Yes, ma'am.
Okay, great. Thank you for your reply. So let's move towards next thing, transfer vector. So here again my animation sequence goes wrong. So I'll put all the things here. So next, first you are generating relocation bit, second you are generating transfer vector. So just consider the program here given in the first half. This is your input file suppose. For this assembly program, your assembler will generate the output. Okay. So the second half here, it is the output generated by your assembler. Now you guys are well aware with all the statement except this extern and entry, right? Extern keyword right now. So I'll tell you what we are doing here with these keywords. Rest is as it is we have learned in first unit. Main is the label associated with start pseudocode. No operand value means your LC starts from 0. Then load instruction is of 4 byte, BAL is of 4 byte, ST is of 4 byte, BC is of 4 byte, DC will take 4 byte likewise. Okay, and end is a pseudocode. So I have already done the translation of rest of the code. Okay, but when you are having extern keyword, so you have to create entry in a transfer vector for each extern and entry symbol. Okay, for each extern and entry symbol, entries are created in a transfer vector. So transfer vector is a space where you are keeping information about linking with the external subroutines. So external symbol SQRT, external symbol ERR, these are the external routines which may be called here. See here, BAL is giving call to SQRT. So you are going to branch to SQRT. BC is also going to branch to ERR. So these are the jump location to outside routines. So how these outside routines will be linked? So your subroutine linkage concept come in picture. External keywords are used, SQRT and ERR. Okay. So for each entry of this extern, for each symbol associated with extern keyword, we are creating entry in a transfer vector. And now look at here, start is not having any operand value. So if no operand value given, your LC starts with 0. So your relative address is 0. Now observe the right hand side of your slide. I have created a table where we are keeping column as relative address, relocation bit, and the actual object code. Okay. So whenever you start processing, what is the role of start pseudocode? Start pseudocode will set location counter to 0. So that 0 is done. I am putting that arrow over here. Okay. After that, main will be added in a symbol table. So assume there is symbol table where entry of this label is done in symbol table. After that, second instruction when you read, it is a extern pseudocode. Extern pseudocode means you will find its entry in a pot table. And then after whatever symbol coming with extern, that SQRT symbol will be added as the object code area. See here. Okay. So first entry of transfer vector is created. It is again a 4 byte, starts from 0th. Okay. So 0 to 4. These are the first 4 bits will be occupied by first external symbol SQRT. Right now you don't know what is the address of SQRT. SQRT main memory में किस address पे रहेगा? You don't know, right? So that's why I have just added a name of symbol itself. And here I'm saying no relocation required. Now why relocation not required? Because in this program अगर आप main का starting address change करोगे instead of 0, if you make it 500, the address of start and SQRT and error will not change क्योंकि वो separate routines है, उनके खुद के different addresses रहेंगे. So अगर मेरा main का address change हो रहा है, I don't need to do any adjustment over here. That's why my both the relocation bits are 0 0. So first half and second half of this line will not require any relocation. Try to understand the significance. Huh? Starting address of this main routine changed, so this symbol 1 will be changed because ये address change हो सकता है. But SQRT and error बाहर है. They will have their own addresses. So which will not be modified if you change the address of mains routine. Okay, that's why my relocation bits are 0, 0. So first 4 bytes of entry is done. So LC will be updated by 4. So 0 plus 4, your next LC value is 4. Blue color में दिखाया मैंने. Again, you scan the input file, that is extern ERR. Again, extern found in pot sudo pot table. So you will create the entry of ERR here. Location counter 4 onwards. So ERR symbol stored here. उसका address नहीं, इसलिए हम symbol name itself store कर रहे हैं. And like SQRT, it is not dependent on your main routine, so no relocation required. So this line will take further 4 bytes of data. So 4 plus 4, next value of LC is 8. And then scan the next line of the input, load 1 comma 0, sorry 1 comma 1. So L is having its own mnemonic and all, so you will search it in a mnemonic table and all those translation will be done. One will go in a symbol table. So manually abhi फटाफट आपको आना चाहिए. And now if you observe here, this L and this will take first half of your instruction where no change is required, no relocation required. But this one is going to take memory space whose address is dependent on. So one is dependent on your starting address, right? अगर मेरा main 0 है तो 1 का address let's say 24 है. अगर main का address 100 हुआ तो 1 will be at 124th location. So need to be relocated. So my relocation bit for second half set to 1. B1 0 है but B2 1 किया मैंने यहाँ पे. I recall the previous slide. So this one indicates second half of this instruction needs a adjustment. So second half means ये वाली space. Here I am not using pseudocode. So there is no base register concept. So physical address ही आपका offset रहेगा. Okay. That's why 24 direct लिखा है मैंने. This will take again 4 bytes. So 8 plus 4 next location address is 12. जहाँ पे आप next instruction store कर रहे हो. BAL 14 comma SQRT. So BAL and 14 don't need any relocation. So again my first B1 bit is 0. But SQRT is a symbol which is available at some other address. So if that address is changed, the address value to this location will be changed. And that's the reason I have to make it relocatable. Okay. So right now SQRT का address आपके पास नहीं है. But that will be updated here in transfer vector at the first location in transfer vector in future. So I am giving the address of that here right now. Linking information दे दिया मैंने कि from where you are getting the address. So 0th location of transfer vector will give the address to this field. So it is dependent on that 0th location. And that's we need to relocate. So इसलिए यहाँ पे 1 कर दिया. Again it is taking 4 bytes. So 12 plus 4 next is 16. Where ST will be stored. So ST1 comma symbol 1 depend on main subroutine. So again my relocation bit is set to 1. 16 plus 4 20. Next location is 20th location where at BC 14 comma ERR. So ERR is again a external routine which need to be modified. And who will give the address? Linking information कहाँ पे मिल रहा है ERR का? This extern ERR entry जो आपने ट्रांसफर वेक्टर में लोकेशन 4 पे की है. And that's the reason I have to put the address of this here. These two are linked. And that address is change means you have to relocate. That's why my second half of this instruction is relocatable. Then your 1, symbol 1 is stored at location 24. So this 24 address is inserted here as well as here. Right? Physical address of symbol 1 is added here. Direct pass to means आपके L, BAL, ST आप hex code से replace कर सकते हो. No issues. Just for understanding, I kept it as it is. And then here we are keeping 1. Value of that symbol is 1. F1 है ना यहाँ पे. In a single quote you have 1. So that value is added here. वो यहाँ पे जा रहा है. And no relocation because 1 का value change नहीं होगा if you are changing your starting address. And then current instruction will take 4 bytes. So 24 plus 8, 4 will be 28. So this is how transfer vector and object code is generated for given program by your relocating loader. If you remember, this single example is more than sufficient. Okay. You can create your own example if you understand the concept of extern keyword. For each extern keyword, entry is created in a transfer vector which is of 4 bytes. So symbol name itself stored over there. And along with relocation bit, you are keeping the LC values. Relative address is your location counter values. And don't forget that. This is your LC. Nothing else. So external references of these routines are handled here with the help of extern. So subroutine linkages are used in this relocating loader, that is BSS loader. Okay. So same example. Now I'm going to take this transfer vector and object code on next slide, and I'll show you how relocating loader will load that program in a main memory. So try to bear again. Transfer. So actually, I was using some animation over here. So if same code I have fetched from previous slide, my transfer vector is there. Now, if you observe how many bytes are utilized by your transfer vector, 0 to 4 and 4 to 8. So this transfer vector is of, just a minute, 8 bytes basically. This is your 8 bytes of data. TV is of 8 byte. Try to bear with it, okay? And then rest of the space is taken by your object code. So exact length of your object code you have to compute. So subtract the end value 28 minus start value is 8. आपका object code 8 से start हो रहा है up to 28. So 28 minus 8 program length is of 20 kilobytes. Transfer vector is of 8 kilobytes. Okay. So your assembler has given the information transfer vector, relocation bits, object code, program length, and the transfer vector. So entire info is given by your assembler. And now you're ready to use your BSS loader. Okay. So how the BSS loader is going to help us? So BSS loader will load the program. Let's say main routine starting address is allocated as 400. Assume it. Okay. We have done the translation by assuming starting address as 0. But now we have got the memory location in a main memory area which is free from 400 onwards. So main routine is loaded at 400. Main routine. You're talking about your main routine. SQRT, if you observe, it is starting from location 428. ERR starting from location 500. So all three modules are loaded by your loader in a main memory. Okay. Now your first instruction. So whenever you are loading your transfer vector to main memory, each transfer vector entry is replaced by branch instruction, branch on count instruction. Okay. So here for first SQRT entry, you have written branch. So now where is your SQRT? SQRT is at location 428. If you observe here, SQRT आपका 428 पे. So I'll replace कि BC means branch कहाँ पे करना है आपको 428 पे. So I'm writing BC is a branch instruction, branch to location 428. Okay, and the address of next instruction return कहाँ पे करना है? That is stored in register 15. Address of next instruction, that is 404, will be stored in the register 15. Similarly, load the next statement, that is ERR. So again you are writing at location 404 BC. So remember, for each transfer vector entry you have to write one branch instruction. So BC 15, 500. Now this ERR subroutine is loaded at location 500. Observe this space. This is the ERR area. I'm writing some lines over here, red color lines. So this 500 location is a starting location of ERR subroutine. So आपको जब call करना है, you will jump to the location 500. And the return address will be stored in register 15 again. Then object code is loaded. So your next instruction from 8th location will be loaded at 408. So see, आपका translated address था 8, but now you have to load it at the location 408. Okay, and your current instruction needs a relocation because its translated address for the symbol were 24, जो अभी 424 पे है. So see, loader will adjust this. Base address will be added here. So 424 is the location. And then write to that line. Similarly, 12th location 16, 420 and 424 is returned. Okay. So if you observe instead of 0, what I am writing? 400. क्योंकि मेरा 0 किस पे मैप हो रहा है? 400 पे. Look at this. I'll use a different color over here. Okay. So I can show you the line. This 400 is mapped with, sorry, 0 is mapped with this 400. Fine. So in this way, you have to write 0 is replaced by 400, 4 is replaced by 404, 24 is replaced by 424. So this is done, this relocation is done by your BSS loader. Okay. Then your SQRT code will be loaded in this area 428 onwards, then 500 location onwards, ERR is present. So you have loaded entire code in this memory and the execution will start. So executable statement कहाँ पे है आपका? This is your executable statement. ये जो है first two lines, these are your transfer vector entries which we cannot execute directly. So the control will be transferred to the first location, first instruction location. So first instruction का base address क्या है, effective address क्या है? 8. So 8 is mapped to 408. Here onward your execution will begin. So your processor will read first instruction, load the value of memory location 428, sorry 424. So 424 पे क्या है value? 1. So this 1 is loaded in a register 1. Register 1 में value गया 1. Okay. Then you are going to jump branch to the location 400. So you will be branching to the location 400. Okay. Just a minute. Yeah. So 400 means कहाँ पे है आपका 400 location? See here, this golden arrow or green arrow. 400 means BC statement at 400 location. And BC से कहाँ जा रहा है आपका control? 428. Branch to the location 428. So it's a two-step journey. If you look at original program, आप branch to SQRT ही कर रहे हो, but उसका direct address आपके पास नहीं है. But you know the address in a transfer vector, that is 400. And the 400 location is helping you to go to the location 428 जहाँ पे आपका SQRT statement है. Then your SQRT procedure get executed. Once your execution is over, your control goes back to next statement, that is 416. You'll execute, store the result to the 424th location again. Then you are branching to the location 404. So 404 means it's again a, let me change the color. 404 means you are going to jump to the location BC. Look at that purple color arrow. 404 is a BC 15, 500. So 500 means आप कहाँ पे jump कर रहे हो? This ERR subroutine. So your control goes to ERR. ERR will be executed. Control goes back to the next location where your symbol 1 is defined and then end of the program is reached. So this is how your processor will execute the program once you load them in a main memory area. So I hope you guys have understood how BSS loader is loading. The key points to remember is each line of transfer vector is returned to main memory as a branch statement BC. Okay, BC 15, address of that subroutine. After loading, you will definitely get the address of subroutine. Okay. Then same way for ERR, next subroutine address. So branch instruction is written. Then onwards, rest of the object code is written. And wherever the address dependency is, relocation bit is guiding you to relocate. So if you observe, all these 4 instructions are relocatable. If you look at this area, all the bits second half is relocatable. So 24 की जगह आप लिख रहे हो 424. For 0 you are writing 400. For 24 you are writing 424. For 4 you are writing 404. So this is how you have relocated, your BSS loader have relocated these segments, these values. And the loading is done. After that, execution will be done by your processor. I have just shown the sequence how execution time you are switching from the location 404 to 500. So do you have any queries related to BSS loader? I hope you have understood the working of BSS loader. And most of the time theory questions are asked, what is relocate, why we use relocating loaders. So it helps you to overcome the drawback of absolute loader. Then explain how binary subroutine, symbolic subroutine will requires the input from assembler, that is transfer vector, object code, program length, relocation bits, and how that info used by BSS loader to load the program in a main memory. So this slide is the answer for that. You can load that program likewise, which I have shown on the screen. So do you have any query in BSS loader? Please let me know. No questions, or you have not understood? Please frankly let me know. So here our BSS loader is ended along with the drawbacks. If you're not having any queries, I can discuss the drawbacks of BSS loader. Okay, no queries from your side, so we'll move ahead. So drawbacks of BSS loader are like, as you're along with object code, as you're adding transfer vector. Transfer vector is helping us for TV. Transfer vector is helping you for relocation, sorry, linking purpose with external subroutines, right? So you are creating additional entries along with your object code. So in previous example, object code were taking 20 bytes KB, kilobytes, but transfer vector is taking additional 8 kilobytes of data. So that will increase the length of a program. So transfer vector increases your length of a program. Okay. So sorry, bear with that line. Okay. Then transfer vector is used for linking purpose, right? Not for loading purpose. So it is helping you to link with the original external subroutines, right? And for which we are consuming extra space. So utilization of extra space is not a good thing. That's why it is a drawback. And BSS loader can handle multiple processes, multiple programming subroutines, but no multiple data segment support given. Data segment एक ही support करता है. So all the procedure data need to be kept in single segment, and that is another drawback. So BSS loader first drawback is it is used for linking, not for loading and storing external data. So consuming extra space will be a drawback, disadvantages, and it is not supporting multiple data segment.